At 218 degrees Celsius, Kc for the reaction shown is 1.2 times 10 to the minus 4. Calculate the equilibrium concentrations of ammonia and dihydrogen sulfide if a solid sample is placed in a closed vessel and allowed to decomposes until it reaches equilibrium. All right, so we have a heterogeneous equilibrium. Solids and liquids don't appear in equilibrium expressions, so this is all about the concentration of the products raised their stoichiometric coefficients. For every X amount of the solid I lose, I make X amount of ammonia and X amount of dihydrogen sulfide. So this is what was set up, right? This thing is decomposing, and as it decomposes, it makes ammonia and dihydrogen sulfide. So these are the equilibrium concentrations. We plug these into the law of mass action. And we solve for X. So X times X is X squared. If I take the square root of both sides, I solve for X. So this is the equilibrium concentration of the ammonia and the dihydrogen sulfide for this reaction. For the reaction, iodine reacting with bromine to make 2 iodine bromides. The Kc is 280 at 150 degrees Celsius. Suppose that 0.5 moles of the product, iodine bromide, is in a 2-liter flask is allowed to reach equilibrium. What are the equilibrium concentrations for the reactants and the products? All right, so we've got a reaction here where I've got all products and no reactants. So what's going to happen here is this is going to slide backwards to reach equilibrium. So according to the coefficients, for every 2 iodine bromides lost, I'm going to make 1 bromine and 1 iodine. So for every 2x of iodine bromide lost, I'm going to make X amount of bromine, X amount of iodide. All right, X in this case is going to be small, right? This is a spontaneous reaction going towards the products. So I plug these concentrations into the law of mass action. Concentration of the iodine bromide raised to the second power, divided by the concentration of X times X is equal to 280. All right, in a situation like this, we want to try to not solve for a quadratic, right? So if I take the square root of both sides, this will make this easier to solve for. I can now multiply both sides by X and collect terms and solve for X. This will be the iodine concentration, the bromine concentration. Subtract 2X from what I started with in terms of iodide bromide, and I'd get the concentration of iodide bromide. All right, consider ammonia reacting with oxygen to form nitrogen monoxide and water. This is an exothermic reaction with a release of 904.4 kilojoules. How does each of the following changes affect the yield of nitrogen monoxide at the equilibrium? Answer, increase, decrease, or no change. All right, nitrogen monoxide is poisonous. All right, so there could be a perfectly good reason for decreasing the amount of nitrogen monoxide, or I guess if you wanted, increasing the amount of nitrogen monoxide. So if we look at situation A, increase ammonia, what will that do to the concentration of nitrogen monoxide? Well, this brings up what's called Le Chatelier's principle. Le Chatelier's principle states that if I stress the system, in this case by adding more ammonia, the system will respond to try to get rid of that stress. So if I increase the concentration of ammonia, the system will be driven forward in order to get rid of it. And in this situation, you'd increase the concentration of the nitrogen monoxide, and this is how it would shift. All right, looking at B, increase water. All right, so as I said a few minutes ago, nitrogen monoxide is toxic. So let's say I want to get rid or lower the concentration of nitrogen monoxide. One way of doing this would be to add water. All right, so looking at the law of mass action, let's say I increase the concentration of water. the system responds to try to get rid of that increase, right? I've put the concentrations out of balance, right? Q is no longer equal to K, so the system has to respond to try to get rid of that increase. So that'll drive it backwards, and that will lower the concentration of NO. If I add more water, increase the concentration again, the system will respond to try to get rid of that increase in pressure or increase in concentration by driving it backwards and decreasing the concentration of nitrogen monoxide. So this is how it works. Increase the concentration of water, decrease the concentration of nitrogen monoxide. Looking at C. This is a good way. All right, decrease the concentration of oxygen. If I can pull oxygen out of this equilibrium, the system will respond to try to replace the oxygen. So lowering the concentration of oxygen, pull it back toward the oxygen, right? The system tries to replace it, and that'll lower the nitrogen monoxide concentration, raising the ammonia concentration. So if I keep doing this, right, if I keep pulling oxygen out of this equilibrium, eventually I really lower the nitrogen monoxide concentration and, increase the ammonia concentration. So again, you want to drive this reaction backwards, keep removing oxygen from the equilibrium. All right, D. Decrease the volume on the container. All right, well, decreasing the volume is the same as increasing the pressure. So if we increase the pressure on the system's going to respond to try to get rid of that pressure. So this will drive the equilibrium toward the side with less moles of gas. So again, if I want to get rid of nitrogen monoxide, increasing the pressure will drive it back towards the reactant side, lowering the NO concentration. E, add a catalyst. A catalyst has no effect on the position of equilibrium. It lowers the activation energy in the forward direction just as much as it lowers the activation energy in the reverse direction. So it has no effect overall on position of equilibrium. Now, increasing temperature. This was an exothermic reaction. All right, so it's almost like energy is a product here, right? It's an energy releasing process. So if I increase the temperature, or another way of looking at it is increasing energy, the system will respond to try to get rid of that and drive it back towards the reactants, again, lowering the nitrogen monoxide concentration. So these are things you need to know, right? It's important, right? We want to shift the equilibrium in the direction we want to shift it. So 62, put a little star in it. Know how to do this. Looking at 67, ozone decomposes to molecular oxygen in the stratosphere according to the reaction. All right, so this is a very spontaneous reaction. Would an increase in pressure favor the formation of ozone or oxygen? All right, so the way this looks, I've got 2 moles of gas going in and 3 moles of gas coming out. So increasing the pressure will drive this backwards. So if you wanted to keep ozone and lower the oxygen pressure, you could increase the pressure on the system. It'll drive this equilibrium back towards the side with less moles of gas.